A rough model of the greenhouse effect can be described as follows. Visible light that comes from the sun will pass through the Earth's atmosphere because the atmosphere is transparent to visible light. That visible light is in all the different colors, red and blue and green and so on. Some of this light that strikes the Earth will be scattered, in other words, reflected away, while other light will be absorbed by the objects that it strikes. Think about what you are looking at when you see a tree in the forest. On a bright sunny day, all the colors of light are striking the leaves of that tree. You have red light and purple light and green light striking the leaves of that tree. However, the tree will absorb the red light and the purple light, but the tree will scatter or reflect the green light. It is this green light that's scattered by the leaves of the tree that enters your eyes, and this is why you perceive a tree to be green. So if we were to look at a picture, we have all the different colors of light coming from the sun, and we could say this light strikes a forested patch of the earth. That forested patch of the earth will absorb the red light and the purple light and the blue light that strikes it, but the green light will be scattered, most of it escaping back into space. Now, we could ask the question, the energy contained in this red light and the purple light and the blue light, where does that energy go? The energy that is absorbed by whatever object it strikes will tend to increase the temperature, increase the thermal energy of the object. This object, because it is at a non-zero temperature, will then emit blackbody radiation. So let's suppose we have an object at a temperature of 287 Kelvin, which is roughly the average surface temperature of the Earth. Let us ask then, at what wavelength will an object at this temperature give off the most light due to blackbody radiation? To answer that question, we will apply Wien's law. I could say the wavelength at which an object gives off the most light due to blackbody radiation is 2.9 times 10 to the minus 3 divided by the temperature of the object. We are assuming the object has a temperature of the average surface temperature of the Earth, which is 287 Kelvin. When I plug these numbers into a calculator, I get the wavelength at which this object emits the most radiation will be 1.01 times 10 to the minus 5 meters. If I convert this to microns, I find the wavelength is 10.1 micrometers. So what does this result mean? Well, it turns out that carbon dioxide gas is transparent to visible light, but carbon dioxide gas is opaque to this wavelength of light, which is in the infrared part of the spectrum. So for the same reasons that you learn about in spectroscopy, when certain atoms and molecules will absorb certain colors or wavelengths of light, but allow other wavelengths of light to pass right by them, the light that is given off from objects on the surface of the Earth in the infrared part of the spectrum will be absorbed by some of the gases in the Earth's atmosphere, such as carbon dioxide. Now, this carbon dioxide will temporarily be in a higher energy state, but then this carbon dioxide will fall back to a lower energy state and emit a photon of light of this wavelength. What direction will this photon travel? Well, it's essentially random. Some of these photons will continue to travel out of the atmosphere and escape away into space, while other photons might travel back towards the ground. Now, we need some amount of greenhouse effect to keep the Earth warm, but if there is too much carbon dioxide, we will have more of these photons in the infrared part of the spectrum becoming trapped in the atmosphere. And this will tend to increase the temperature of the Earth as the carbon dioxide builds up more and more. This is the reason that having ice in the Arctic and Antarctic is a very powerful tool for combating climate change. Because this energy that strikes the icy regions of the Earth is able to almost entirely be reflected back into space, this energy from the blue light and the purple light and the red light is not going to contribute to an increase in the temperature of the Earth. In this example, we have two samples of metal, one of zinc and the other of cadmium. We shine ultraviolet light on these two samples, and we are first asked to determine which metal will emit photoelectrons with a greater maximum kinetic energy. When I think of the photoelectric effect, I think of energy conservation. When we shine light on a sample, the energy of that light is given as hc over lambda, or if you prefer, you could write the energy of the light as h times f. The electrons in the metal will absorb that energy. So we could ask, where does that energy go? Some of that energy will go into liberating the electrons from the metal, and if there's any energy left over, that leftover energy goes into the kinetic energy of the electrons as they fly away from the metal. The more tightly bound an electron is to a metal, the more energy it takes to liberate that electron, and therefore there will be less energy left over to go into that electron's kinetic energy. The work function of a metal is the energy by which the most loosely bound electrons are bound to that metal. Looking at the two values of the work function, I see that the work function of cadmium is less than the work function of zinc. Therefore, it takes less energy to liberate the most loosely bound electrons of cadmium. If it takes less energy to liberate the most loosely bound electrons in cadmium, there will be more energy left over to go into those electrons' kinetic energies. Therefore, cadmium will produce photoelectrons with a greater maximum kinetic energy. In the next part of this problem, we are asked to find the maximum kinetic energy of the photoelectrons emitted by these two samples when they are exposed to light with a wavelength of 275 nanometers. We will use the photoelectric effect equation, and I have already went ahead and converted Planck's constant from units of joule seconds to units of electron volt seconds. When you work with the photoelectric effect, it is very common for energy to be in units of electron volts instead of joules. So if I were to plug numbers into this equation, h times c is Planck's constant times the speed of light. So I would have 4.14 times 10 to the negative 15 times the speed of light, which is 3 times 10 to the 8, divided by the wavelength of light shined on the sample. So that would be 275 nanometers. So I will have 275 times 10 to the negative 9 meters. And then that is equal to the work function of the metal that we are considering, plus the maximum kinetic energy of the photoelectrons emitted by that metal. So if I first consider zinc, I will have 4.33 electron volts plus the maximum kinetic energy for zinc. Plugging numbers in a calculator, we find that the maximum kinetic energy of the photoelectrons emitted by the sample of zinc is going to be 0.186 electron volts. If instead we were to consider the photoelectrons emitted by the sample of cadmium, everything would be identical, except we just have to change the value of the work function. So now cadmium has a work function of 4.22 electron volts. So I will write 4.22 here. And I am now talking about cadmium. And if I plug these numbers into a calculator, I find that the maximum kinetic energy of the photoelectrons emitted by cadmium is 0.296 electron volts. Typically, we do not think of everyday objects such as chairs and dogs as waves, but any object can be treated either as a particle or as a wave. For wave-like behavior of objects to be prominent, you will typically need the wavelength of that object to be comparable to the width of the slit that that object passes through. For example, in the Young's double slit experiment, you would want the width of the slits that the light passes through to be comparable to the wavelength of the light that you are using. In this problem, we are considering a 65 kilogram student that passes through a doorway with a width of 76 centimeters, and we are asked at what speed should the student be moving for the wave-like behavior of that student to become prominent. In order to address this question, we will use the de Broglie wavelength. The de Broglie wavelength of an object is given as lambda equals h over p, where p is the momentum of the object and h is Planck's constant. Momentum is mv, mass times velocity. So I will want the wavelength of the student to be comparable to the width of the slit that that student passes through. In this case, 0.76 meters, the width of the doorway. So I will write 0.76 is equal to 6.626 times 10 to the minus 34, divide by the momentum of the student. Momentum, 65 times the student's velocity. 65 for the mass times v. Plugging these numbers into a calculator, we find that the velocity of the student is going to be 1.34 times 10 to the negative 35 meters per second. In the second part of this problem, we are asked to determine how long it would take the student to travel 1 meter when moving at this speed. So I will just say speed is equal to distance traveled over time. If I want to be incredibly formal, I would say x equals x naught plus v naught t plus 1/2 at squared, but the student is not accelerating, so I'm just going to revert to this simpler equation. So I could say 1.34 times 10 to the negative 35 is equal to the distance the student travels, which we want to be 1 meter, and we are asked to find the time it would take the student to travel this distance. So rearranging this equation, I could say t is equal to 7.46 times 10 to the 34 seconds. To quickly compare the time scale it takes the student to travel 1 meter to the age of the universe, which is 4.32 times 10 to the 17 seconds, I will divide 10 to the 34 seconds by 10 to the 17 seconds. I'm not really going to worry about these numbers multiplied by my powers of 10 because I'm just trying to make a quick estimate. So 10 to the 34 divided by 10 to the 17 will give me 10 to the 34 minus 17, which gives me 10 to the 17. So it will take the student approximately 10 to the 17 times the age of the universe just to travel 1 meter in distance. The fact that we have a 10 to the 17 here and the age of the universe is 10 to the 17 seconds is just coincidence. So if I were to say that 10 to the 3 is 1,000, 10 to the 6 is 1,000,000, 10 to the 9 is 1,000,000,000, 10 to the 12 is 1,000,000,000,000, 10 to the 15 is 1,000,000,000,000. That means that it will take the student approximately 100 quadrillion times the age of the universe just to travel 1 meter. In this example, we have an electron with an uncertainty in its position of 0.01 nanometers. Therefore, I could write delta x is equal to 0.01 nanometers, but we always want to be working in meters, so I'm going to convert this value, and I get 0.01 times 10 to the minus 9 meters, which is equal to 10 to the minus 11 meters. From the Heisenberg uncertainty principle, I can find the minimum uncertainty in momentum of this electron. I would write delta p delta x is going to be at least h over 2 pi. We already have delta x. I'll bring delta x to the other side of this equation. So therefore, I could write the uncertainty in momentum of this electron will be at least 6.626 times 10 to the minus 34 divided by 2 pi divided by the uncertainty in the electron's position, which is 10 to the minus 11 meters. When I plug these numbers into a calculator, I get the uncertainty in the momentum of the electron will be at least 1.05 times 10 to the minus 23. And because I'm talking about momentum, my units will be kilogram meter per second. In the next part of this problem, we are asked to find the kinetic energy of an electron if an electron has exactly this momentum. It is possible that the uncertainty in the electron's momentum is greater than this value, but the uncertainty in the electron's momentum will never be less than this value, provided the uncertainty in position is 10 to the minus 11 meters. So we will set P is equal to 1.05 times 10 to the minus 23. Now, if this is the momentum of the electron, what is the electron's kinetic energy? I could write kinetic energy is equal to p squared over 2m. You could see this if you plug in p equals mv, we would have mv squared divided by 2m. And if I do some algebra, I would have 1/2 mv squared for kinetic energy. So plugging this value in for the momentum, and the mass of an electron is 9.11 times 10 to the negative 31 kilograms, I could see that the kinetic energy of the electron would be 1.05 times 10 to the minus 23. Then I square that value, divided by 2 times 9.11 times 10 to the minus 31 kilograms. The mass of the electron we would just look up in a table in the back of a textbook. And then we find the kinetic energy of the electron will be 6.1 times 10 to the minus 17 joules. If I were to convert this energy into electron volts instead of joules, I would find then that this energy is also equal to 380 electron volts.